right then. So yeah, we're going to be covering scheduling processes today. So what's on the agenda? So firstly, what is the point of scheduling? What are the prerequisites for good scheduling? The types of scheduling and what features are used in determining the next running processes during scheduling and how we can improve a scheduler. So first of all, what is scheduling? Now, scheduling allows for running processes in a fair and ordered way, i.e. the order of running interrupts, processes, threads, and things like that, in order to not cause inconsistencies within the system. For example, we don't want threads running before or after each other in a way that they shouldn't be. We don't want processes to be interrupted when they shouldn't, and we want everything to be running in the best way possible, um, such that we're not even limiting other processes from running as well. So you can see here we have like an image of all the different types of CPU scheduling. So we have, obviously, firstly, we split the types of scheduling into preemptive and non-preemptive. Obviously, preemptive being where we can relinquish the process control at any time, which is good for things like when we want to run a process and then let's say that process will go into an IO operation or an input-output operation, and then we wait that process. When we preempt that process and then we put another process onto the CPU, we increase the CPU utilization time. So it's really good for things like that. Now, you can see as you go more down into this sort of tree of different types of scheduling, we'll move on to the non-preemptive first, obviously, non-preemptive being the opposite of preemptive, where we're not sort of scheduling, um, sorry, we're not relinquishing the control of the process to the OS. So things like first come, first serve, shortest job first, longest job first, high response ratio next. Highest response ratio next, I'm not going to cover, nor I'm going to cover longest job first. But everything else on here, I will be covering in some detail. Actually, I also won't be covering longest remaining job first as well. But yeah, we also have on the preemptive side, priority scheduling, shortest remaining job first, and round robin. At least most of these should be covered. I believe six of them on the screen are covered um, in these slides, and there's a bit more than just this. But yeah, so when we schedule processes, right, obviously we need some sort of ordering. Now, this ordering can come in many different ways. And you can think about it like, let's say, for example, you want to schedule some events into your calendar, you usually, if you're quite productive, you would want to schedule them priority order, right? So you need some sort of way to prioritize them, and you can have a queue for that, right? So we can have many different types of queues for many different types of processes. We can have things such as device queues. These device queues will contain processes that are currently doing I/O operations, or like disk access operations, things like that. Um, or hardware accessing. You also have job queues, where these job queues will contain ready processes. Going back to yesterday, if you weren't here, that's completely fine. But ready processes are processes that have their memory initialized and are ready to be context switched to. If you didn't attend the context switching video yesterday or the live event yesterday, or if you haven't watched the video, I highly recommend you do. That's on the Texiland channel. Hopefully, Shay can put it in the top right when it's being edited. But yeah, okay, cool. So, what are the prerequisites for good scheduling? So, there's two prerequisites according to our slides. So, oh, thanks, Shay. So yeah, you can go ahead and watch that processes one. Um, So, first of all, preemptive scheduling. So, preemptive scheduling, like we mentioned before, preemption, right? The sort of way of features being able to, I mean, not features, the way of processes being able to be relinquished off the CPU and gaining control. So the OS will gain back control, right? So, like I said before, it will allow for task fairness. It will allow for these processes to have time slices such that no process can hog the CPU, i.e., we can kick those types of processes off the CPU. So there'll be fairness between all of these different processes, right? And we can also prevent processes from starving. Now, I'll go into starving or starvation into a bit more detail later on, um, but I'm sure you can sort of guess what it means. Uh, so the next prerequisite for good scheduling is CPU I/O burst cycles. Now, not to understand this, you gotta sort of break it down a little bit. Obviously, CPU and I/O, we already know, right? Burst cycles. Obviously, burst time is the time or the full time a task needs in order to run on the CPU and be completely finished with it. So it's also defined as the turnaround time for a task to run on the CPU with no distractions or no context, which is nothing else. So just be that process running on your CPU. Now, when it comes to processes that have I/O operations, 90% of the time you can predict the burst time of the process. So instead of having to context switch in some cases back to like your let's see, like your IOQ and then back, and just constantly doing a lot of context switches, you can sort of allocate enough time for a sort of process such that you don't need to context switch, i.e., reducing the latency because obviously context switches are expensive, and hence you're able to improve or like reduce the latency in that way. I can see you have a comment in the chat. So you're saying that non-preemptive scheduling algorithms are bad. What about high priority interrupts? Um, I mean, we can, yeah, I mean, I guess I can get into it. I think I'll talk about it in the next few slides, but just to give you a brief sort of answer to that. When we talk about non-preemptive scheduling, obviously we have a lot of these different things, right? So you have shortest job first, first come first serve, longest job first, etc. Now these sort of things where we can't actually take control of the process, and like allow for some sort of concurrency, then it's going to be pretty weird for processes to run in such a way that we allocate fair time to a CPU. So what I'll do is I'll actually go into it now. So we have a few types of sort of simple scheduling algorithms. Now these are the ones that aren't usually used in real life, or at least they were used, but they're not used in like modern um, sort of like machines, things like that. So let's get into it. First come, first serve is the first one. Processes are done in order of arrival. If we have a long process followed by many short processes, they suffer from the convoy effect. Let's see what's happening in the chat though. If preemptive algorithms are implemented poorly, then a non-preemptive alternative could be better, I think. Yeah, that's true. But it could be better if a poor quantum time is chosen for round robin, though, for example. Exactly. So, for example, if we have a poor time quantum or poor time slice for round robin, um, let's say like we have a larger time quantum, that means that a process will be running on the CPU for longer, and that could increase the response time for another process. Although you might have a better turnaround time for like an average of the all of your processes, if you want to prioritize response time, round robin's probably a better idea, which is basically FCFS but with preemption. Um, so yeah, we have this long process, let's say on FCFS, and you have many short processes following it. Obviously, your short processes aren't really going to have a good response time, right? Um, it's going to take a while for them to actually be um, sort of the first response or the first update after the submission of the process into our queue is going to be quite long. So this is one of the reasons why we don't use FCFS. Um, Now, going on to shortest job first or shortest job to completion. Uh, like it says in the slides, it solves the convoy effect, but it's not implementable. So essentially, we can't actually predict how long a process will run. Um, there's various things that we can do to predict it, but then at that point, it's not really a good idea to actually use that because a prediction is a prediction. There's times where you can be wrong. Um, so it's not always the best thing to do. But it does solve the convoy effect because we do things in order. We do things from the shortest job to the largest. Now, main difference between what's the full definition of convoy effect? Sorry, I think I missed it. Yeah, sure. So the convoy effect um, is basically when you have a long-running process that will sort of reduce the response time for the other queued up sort of like processes, like the shorter processes. And hence, in this way, it will reduce response time. So that's essentially the convoy effect, if that made sense. Yeah. Okay, cool. So yeah, like I said, it's impossible to know the time a process will take in truth, so we can only predict, and that's not really a good measure. So we don't use shortest job first or shortest job to completion. The main difference between the two is that shortest job first is a non-preemptive method, and shortest job to completion is a preemptive method. So we would essentially relinquish the CPU as soon as we find a shorter job. Now you can also see if we did that with preemption, we'd be doing too much context scheduling, right? Context scheduling, context switching, sorry. We would be doing too much of that because as soon as, let's say we have two processes, each of them take 5 seconds, as soon as one gets down to like 4 seconds or something, oh, like a truck convoy. I'm not sure how it actually came up as, but maybe it is. Yeah. I just know it's called the convoy effect. But yeah, no, let's say we have like two processes, 5 seconds each. Let's say one gets to 4 seconds. Um, when that process gets to 4 seconds, if we had preemption, we would switch to the first process. I mean the other process, sorry, which is 5 seconds. That will go down to 4 seconds and then down to 3 seconds, and then we context switch again. And then imagine that for like a really, really long process. It's going to be too many context switches. So this is also another reason why it isn't good and it isn't used. The next one, it would be single queue priority scheduling. So this is like getting, like if you think back to DSA, we had heaps, right, which were in a way priority queues where you could either have the maximum or the minimum node at the top of your queue and then everything else below, right? So with this single queue priority scheduling, you would be able to pull from this queue for the largest priority process. Now, to be fair, this actually is not bad because you're ordering by priority, which is really good. You're not ordering by the length or whatever, because what matters to your computer is the things that it needs, right? It's not about how long it will take. So in this way, it's much more flexible to use priority-based scheduling algorithms. Um, but yeah, a line of trucks, the front holds the others up. Yeah, exactly, Shay. Could lead to starvation of low priority processes if aging isn't implemented. Exactly. And I'll go over onto that in a bit. Um, okay, we've got some more scheduling algorithms. So these are some of the more useful ones. Now, I've included two extra ones just so I can talk about real world implementations of things like aging. So we'll talk about multi queue scheduling first. Seems like I've spelt it wrong as well, but please don't mind that. Okay, so multi-queue scheduling. You have several, usually preemptive queues, all with a priority scheduling system. So you have many of these queues, and all of these queues are ordered in priority order. And so you're able to choose the highest priority sort of, what's the word? The highest priority process from each of these. And these sort of queues can be like category specific. So like we were going back to before, job queues, device queues, things like that, right? Um, cool. Now, when you run your computer, I don't know if you guys use Linux or Windows or Mac, but Linux uses something called the CFS. It's called the Completely Fair Scheduler. Now, this isn't examined, sorry, but it's a good thing to sort of understand. So basically, it's a native scheduler. It uses a red-black tree, which is quite very, very similar to an AVL tree, to organize priorities efficiently. Let's see. Is it like multiple ready queues where each queue is like high, medium, or low? It depends on what you would choose it for, as Shay said. Um, so you could do that. You could do other things as well. Like I say, job queues, device queues. There's a lot of different things that you can do, but it would depend on how like you would make your software or how you'd make your OS specific to your machine. So yeah, exactly. It is quite flexible in that case. Back to red-back trees. So yeah, red-back trees are basically quite similar to AVR trees. So you'll have that log of n insertion and getting. Well, getting would be O of one, but yeah, the log n insertion and deletion of nodes. Here, those nodes would be processes, right? Um, and then these processes are sort of ordered by this thing called nice values. So nice values are used quite often in most modern OSs as a way to sort of differentiate between the process priority. If you have nicer processes, these nicer processes are more likely to sort of relinquish the CPU and um, give up the process to another one. As you can see, it's quite a nice process in its nature, right? And you can have less nicer processes that will be more, so they would hog the CPU more in a way, so they're less likely to relinquish a CPU to another process. So a more nicer CPU obviously would have, so these nice values have ranges. A really bad, like not nice, maximum not nice value would be -20, and so a really, really nice, maximally nice value would be 20. Now, you can use this within various different calculations um, in order to calculate several things, which are good for processing and scheduler stuff as well. Was ML, FQ, and A level, or was that multi-queue scheduling? I have no idea. I didn't do A level, sorry. Hopefully, someone in the chat can answer that. But yeah, a minimum scheduler latency is one of the things that the CFS has. So, what do we mean by minimum scheduler latency? A minimum scheduler latency is basically the minimum time slice a process should have in order to prevent context scheduling. I mean, context switching, sorry. I keep on saying context scheduling, but it's context switching. But yeah, context switching. So, like we were talking about in the previous video, a lot of the time you have these expensive context switches that we don't want to do. So in order to prevent this, we have a minimum for this time slice, like a minimum time slice value, such that processes will be able to, one sec. मैं गल्ला बात करदा भरावा. Hmm. Sorry, I'm back. Okay, So yeah, what was I saying? Scheduler latency. Um, it will allow you to have a small time slice such that you're not instantaneously giving up the process back to another one or back to the OS, but you're also minimizing the number of context switches. So it's a good thing to have for a scheduling algorithm. Um, a virtual weighted runtime accumulation system is also there as well. And what we mean by this is that obviously you'll have the physical runtime of your process, but in order to manage your your processes and find a sort of quotient for something in order to help like differentiate between processes is CPU usage time. So we can essentially ensure that each process gets a proportional amount of CPU usage. And we can do this by having a weighted virtual runtime, which is accumulated by weighting the process over all of the other weights, and these weights are usually an accumulation of things like nice values and a lot of other factors, which you don't need to delve into really. But we will multiply this by the physical runtime and add it to like a book kept sort of storage of these runtimes. So we just keep a track of all the runtimes of all the different processes that run on the CPU, which allows us to then have another way of differentiating between the priority of these processes. Okay, cool. MLFQ. So multi-level feedback queue. It's actually the Windows native scheduler. And the way it works is you have multiple queues where you have a sort of hierarchy of queues. It's a hierarchical nature scheduler. So at the top, essentially, think of it like a pyramid in a sense. At the top, you'll have really small queues that are usually used for high priority processes. And at the bottom, you'll have um, really large queues, which are usually kept for longer running processes. So as you go down through your queues, you will have a larger time slice, you'll have a larger queue size, and things like that. Now, essentially, what happens is when you enter like a process into that queue, it will always start at the top, and essentially, it will sort of use up the time slice that it has at the top queue. Remember, the top queue has a small time slice, right? And the bottom queues usually have bigger ones because they're meant for more longer running processes. So as a process uses up the time slice, it will go down. And the good thing about this is that we can firstly differentiate between different types of process natures, right? Like I say, short running, long running, things like that. And we're able to prioritize the ones at the top so essentially, the ones at the top are usually for things that need high response time, such as like, let's say moving a cursor on your screen, right? If you had like a really low priority for that, your cursor would be lagging behind, right? Like it wouldn't be like this, right? Um, so yeah, that's one thing. And yeah, like I say, when you enter the process into the queue, it'll be at the top and it'll go down consistently. But then you might be thinking, if we're going to prioritize a lot of the top ones, what's going to happen to the bottom ones, right? Now, here is when we use aging or priority boosting. So we will regularly or frequently boost the priority of the of the processes that are lower down within the queue. So by boosting the priorities, we're preventing this thing called starvation, where the low priority processes don't get that much runtime when they should, because obviously we want all processes to be equal in a sense. We want to have a fair proportional scheduler for our computer, right? So in this way, we're able to prevent that starvation because we're consistently, or regularly at least, boosting the priority of these processes back up the queues. And this will allow us to then sort of maintain that proportion. So yeah, I'm just gonna have a look at the chat. Okay. Um, Obviously, this from this you can sort of see how aging is used in a real world scenario, right? So it is pretty good. If you are a bit confused, I'd recommend having a watch of some videos on YouTube regarding MLFQ or CFS. They're really good. Like I say, you don't need to know um, these as such, but knowing how they work will give you a really good idea of what a good scheduler is. There's also something that's called symmetric multiprocessing. This is another sort of way in which we can have um, a lot of processes run in parallel and be scheduled. So essentially, symmetric queues exist for each processor, where each processor is scheduled independently with a queue for the specific processor. So each queue has its own scheduler, right? Um, Now, this is just a way for parallel systems to run. Um, there's also a way in which you can have symmetric multiprocessing with just a single shared queue, but obviously it will have its pros and cons, right? So one of the first cons of symmetric multiprocessing is that queues can sometimes have a load imbalance when we schedule these processes to a queue. Or sorry, not when we schedule, but when we add a process to these queues, some of them can be imbalanced, right? Whereas with a shared queue, there's not going to be sort of an imbalance as such. And a shared queue, so one singular shared queue for many processes, it's more likely going to lead to a lower cache affinity. It's more going to be like a soft cache affinity, right? And you're not going to have that sort of like you're not going to be able to benefit from that performance boost that you get with a hard cache affinity, right? Um, there's also other things as well, like a shared queue. It's not really scalable, and when you have like many processes, right? Because obviously, when you think about like a computer, and when we think about OSs and these sort of machines and stuff, um, obviously you look at laptops and stuff like that, right? But you wouldn't actually think about the really, really massive computers on a normal level, right? But this is the kind of thing that you need. Is this scheduling cause for concurrent processing? What do you mean by scheduling cause for concurrent processing? Alright, so if you have multiple cores, yeah, if you have multiple processes, yeah, then on scheduling how they take on CPUs. You mean as in like how the CPUs will like take processes, like how we schedule processes to the CPUs. Yeah, yeah, yeah. So this is like one of those ways in which you can sort of do that. Yeah. So it wouldn't necessarily be concurrency as such, but this is more talking about like parallelism um, specifically, since the concurrency bit is more so done by like a preemptive priority scheduler. That's where you introduce that concurrency because you have these time slices between the processes and then you context switch between processes. That's where you actually get the concurrency. And also, obviously, having the processes run their individual threads and switch between the threads. That's also concurrency in a sense. Is SMP used to handle multiprocessor systems? Yeah, basically. Um, cool. Okay, so features that matter to schedulers. There's a lot of these features, so we'll go through them. So firstly, CPU usage time. Like I said at the start, we want our processes to be proportional, right? So we want them to have roughly similar usage times, given that they all have equal time slices in that sense. Um, we also want CPU processes, oh, sorry, processes that run on the CPU to have a large turnaround time. So by turnaround time, we mean that the time taken for the CPU from start to finish to actually do our process, to actually complete our process, to complete our task. Um, Now, this will involve like time of context switching to other processes and back, things like that. This is like the general time that the process will run, or sorry, not run, but like be within the system until it dies, basically. We also have response time, which is the time at which is the time where we submit the process into scheduling, and the difference between that time and the time where we first get a response. So, like, let's say when we first actually run our CPU, sorry, our process on the CPU. Another thing is throughput, like the rate of which processes run on our CPU. Um, Cache affinity, actually, I'll cover cache affinity later. Total execution time as well, which is the burst time. For a process, how long will it run from start to finish without having to do anything um, in terms of like context switching or things like that? Like the sort of raw time that a process will take in order to run on our CPU with no distractions. Cache affinity as well is another thing, because obviously this isn't something that really affects schedulers, but it's a feature that matters to schedulers because obviously when we have these schedulers um, and when we do scheduling and we allocate processes to various, I mean, when we allocate processes to various processors or various like CPU cores, right? Then the way in which we allocate them will affect our cache affinity. And obviously, we want to have a good cache affinity, right? We want to have that performance advantage. So having a good scheduler will heavily sort of affect our cache affinity. Um, Also, imbalances between multi-queue scheduled queues is another thing that's caused by schedulers. Um, Essentially, with your multi-queue scheduled queues, as I was saying before, you can have imbalances between the different queues in terms of a number of tasks. Like you could have like let's say 8 cores and one of them has like 50 tasks, but the other one only has one. And so it wouldn't really make sense um, to be in that scenario. You wouldn't want a scheduler that will cause an imbalance between your queues. Another thing is the fairness and priority. So going back to that same thing, we don't want these processes to be unproportional in terms of a CPU usage or runtime, and we want them to be based upon what's actually going to be best for the system for both short-term and long-term usage. So, how can we improve a schedule in general? So, in order to solve load imbalancing issues, we have this thing called pull and push migration. It's quite easy. When you have a queue which has got a lot of processes, we can push those processes to another queue. And likewise, in the opposite way, if we have a queue that has a minimal number of processes, it can pull tasks from the other queues that may have more tasks than itself, and in that way, we're able to solve that imbalance. Another thing is aging. So, like we said, the regular priority boosting of these processes in order to prevent starvation, where starvation the is defined as the process is not getting enough CPU usage, um, and essentially not having the correct or enough of a proportion of the CPU usage. Which scheduling algo are you talking about, or just in general that use queues? Yeah, this is just a general thing to improve schedulers in general. Um, I think at least for all of these, um, you can try go back through the slides and see how you can actually improve a scheduler. I think it's a good exercise to do. And you can see which one actually applies to which scheduler algorithm as well. Um, and also finding a balance between response time and turnaround time as well is another thing. Um, when you have like things like round robin, um, obviously round robin is just first come first serve, but with preemption. So each process within your sort of scheduler or your queue or whatever, it will run a process and then the next and then the next in time slices, right? Until a process is finished and we're just done with it and it gets off the queue. But changing these time slices can actually have a big effect on how your scheduler will work. When you have larger time slices, it means that the processes are able to run on the CPU for longer. And because they're able to run on the CPU for longer, right? That means that the turnaround time will increase. I mean, sorry, decrease. It will be better in that sense. So the turnaround time will decrease, but the thing is, it may increase the average response time of your your processes. Because let's say if we have more, let's say we have a list of 8 processes. Obviously, the last process could be like a really small thing, but if we've entered it into our process, it's going to have to wait for all those 7 processes to finish, right? And so in that way, the response time for process will increase. So finding the balance for your system is something that's definitely needed. Um, and you can actually like change the settings for these manually using commands native to your OS. So Linux has specific commands for various different things, not just scheduling. Um, so for example, we have madvise. We can change the settings of memory that we allocate for specific processes, things like that. And there's a whole bunch of other things, but that's getting into a more different realm of it's not examinable. This is just more of like a different thing. But yeah, there's a lot of different things that you can do in general, but the top 3 bullet points are usually the main ones that are good for schedule improvements. Cool. Um, Thank you very much. If you have any questions, please put them in the chat. If not, I'm just going to end the OBS recording now. So yeah, make sure to like and subscribe. Yeah, and we'll see you in the next video.